Good morning. Welcome to the lecture on design of RCC elements. Today we are going to see about limit state method. We have three methods so far. We have seen about the working stress method and the ultimate load method. Today we are going to see about limit state method. Why we need limit state method? Why not the working stress method and the ultimate load method? Working stress method, it is better at working loads alone. It does not ensure any safety at the ultimate load, but it ensures serviceability criteria. Whereas in ultimate load method, it is giving better safety at ultimate load and it won't guarantee you the satisfactory performance for the durability criteria. That's why to overcome these two criteria, we are going for limit state method. In limit state, the name itself denotes that limit state is nothing but limiting the state. That is, the state showing you the impending failure of your structure so that it ensures both strength criteria at ultimate load and ensures safety for that structure and also the serviceability and durability criteria. That's why we are nowadays using the limit state method for designing our structures. Okay, we have two types of limit states. In that, first one we are going to see about ultimate limit state. We can call it as ultimate limit state or limit state of collapse. In ultimate limit state, we can going to check limit state of flexure, limit state of compression, limit state of shear, limit state of bond, torsion and tension. Flexure, it is meant for flexural members, for example beam. Compression for columns. Compression, it includes uniaxial and biaxial compression also, and for both flexure and compression members it will be subjected to shear. We can also check the shear in this method, and for bond also we can able to check under limit state conditions. Then also the associated with bending, shear and torsion. Then for tension also we can able to check under limit state or limit state of collapse. Then the second condition is serviceability limit state. It ensures the deflection criteria, cracking, vibration, fire resistance and durability. Deflection is nothing but when a member is subjected to loading. For example, if you consider this is a beam element, when it is subjected to loading in the direction perpendicular to the axis of your member, it will be subjected to bending. Okay, it will be subjected to bending. When a load is capturing in the direction perpendicular to the axis of your member, you can call it as flexural member. We have certain limitations on your deflection part. The overall deflection may be around L by 250. When you include partitions and all, we can control your deflections around L by 350. Here, the cracking condition. Cracking, we are allowing cracking of 0.3 mm in limit state method, whereas in working stress method, we are not allowing any cracking. That's why this working stress method is mainly used for crack-free structures. For example, water tank. Then third one, vibration. Mostly we are offering static conditions and dynamic conditions also in our structure to check your vibration and to ensure your safety. When a structure is under vibration, we can check for serviceability limit state, then fire resistance and durability. These are the methods involved in your limit state. Okay, before going into the analysis of your limit state method, let me clear about the terminologies involved in that. Okay, the first terminology is now about the characteristic strength. We are using so many materials like concrete and steel. We need to check the strength of each material and what is the characteristic strength of 28 days. Okay, what is mean by characteristic strength now? If you draw a graph of frequency of your test and your strength of the material, when you check the strength of the material by using the compression testing machine by 150 mm by 150 mm cube size. The cube is laid around 150 by 150. Your concrete is being poured here. You need to check your strength of the material in compression testing machine. After testing, this is the frequency of testing. This is the strength of the material. The curve will be drastically changing. Then you will get some peak value. This peak value, after that it will be drastically slowing down. This peak value, it shows you FCM. FCM is nothing but mean strength of your material, what you are been checking for. Then this is your characteristic value. What is your character? That is the strength of the material, that is FCK. FCK is nothing but, as per IS 456-2000, FCK is nothing but characteristic compressive strength of concrete for 28 days. 28 days. It is being tested in 150 by 150 mm cube size. Okay. What is mean by characteristic strength now? Characteristic strength is denoted as strength of the concrete below which not more than 5% of the test results are expected to fall. Your test result should not go beyond your 5%. It should ensure nice strength after reaching the FCK. This is the final value. After reaching your FCK level, it should not drastically drop down. It should attain your ultimate. After that, it should reach your collapse stage. So that we can get the mean strength is nothing but the characteristic strength plus 1.65 times the standard deviation. This is the when you are checking for n number of samples, we have some standard deviation levels. For each and every sample we have some deviation, that's why we are encountering the standard deviation here. 1.65 is nothing but the constant value, because here it is 5%, here it is around 45%. To ensure 45, we have a constant of 1.65 multiplied by your standard deviation. So that this is your characteristic strength of concrete, after which it should not go drastically down. This curve should not go drastically down. This is the characteristic strength of the material. Then what is mean by characteristic load? Characteristic load is that it has 95% probability of not being exceeded during the lifetime of your structure. This is your characteristic load, whereas this is your mean load, this is your characteristic load. So your characteristic load is nothing but the mean load. This is your mean load plus your standard deviation value. You will get characteristic. Characteristic is nothing but this is the ultimate load for a material to be achieved. Okay. When you calculate your design load for your structure, the characteristic load divided by your partial safety factor. The partial safety factor for the material is different. It may be concrete or steel. Concrete, it is around 1.5. Why steel is around 1.15? You may ask why for the concrete it has been larger than the steel. Steel, it has been manufactured under controlled environment, whereas concrete, you have so many materials mixed in it. That's why we are giving some heavier value, because we have some quality restrictions also. We don't do compaction properly, we don't do any vibration properly. Due to lack of workmanship, we are ensuring more safety to the concrete, because concrete fails in brittle manner, whereas steel fails in ductile manner. That's why we are ensuring more partial safety factor for a brittle material. So when we calculate the design load for a member, you can calculate what is the characteristic load for the material divided by your partial safety factor for that load. Now we are seeing about the design strength of the material. The design strength of the material we can calculate it by the formula characteristic strength of the material. It may be concrete or steel divided by your partial safety factor. For the steel it is 1.15, for the concrete it is 1.5. Okay. we have some partial safety factor for loads also. When dead load, we have two types of load we have seen. The major thing, dead load and imposed load. Imposed load we can also call it as live load also. This WL denotes wind load. This is wind load. We have certain combinations of load occurring in our structures, dead load plus live load, and it may be dead load plus wind load, then dead load, live load and wind load. Okay. When we design under limit state of collapse, dead load we can give the partial safety factor value as 1.5. When we go for wind load, it is a real load, that's why we are not ensuring more amount of partial safety factor, we can give one alone. Then for dead load plus wind load, we can give dead load, it may be 1.5 times dead load or else 0.9 times wind load. Here this is 1.5 times wind load. Then when you combine dead load, live load and wind load, it may be 1.2. That is 1.2 is nothing but 1.2 times dead load, live load plus wind load. Okay. When we check for limit state of serviceability, it is for short term effects only. So we are not providing any partial safety factor. It is around 1. 1 dead load, 1 live load, and it may be 1 dead load and 1 wind load. Then 1 times dead load and 0.8 times we can diminish our live load also. We can't expect fully the live load in your structure. So we can get 0.8 times live load and 0.8 times wind load when it is combined. These two are combined. Okay. These are some of the partial safety factor values in our code book. You can see it in our code book IS 456 2000. Okay. These are some of the value terminologies involved in the limit state design. Now we are going to see about stress strain curve for concrete. Stress strain curve for concrete. Okay, let me draw a stress strain graph. This is strain epsilon along x-axis. This is stress sigma along y-axis. This is when you are testing your sample, it will be starting here. Because this is a concrete, you may have some parabolic variation. It won't be in linear fashion because the concrete is composed of homogeneous material. It gives you some parabolic fashion. Likewise, it has been increasing, stress is increasing, strain also increasing. Actually, you may get curve like this. After ultimate, it will be dropped out. This is your actual curve for a concrete testing. When you draw a straight line, it is called as idealized. You are making this actual curve as idealized. This is FCK. When you got FCK is nothing but the characteristic strength when your sigma max will be equivalent to your FCK. When the stress is maximum, you will get the ultimate compressive strength of your material. Then up to 0.1, the parabolic nature will start. Then up to 0.002, that is called as proof strain value, it will be around parabolic fashion only. After 0.003, it will be entering into the ultimate strain value. Here you can see the stress is not increasing, whereas strain alone is increasing. That is, it is entering into the danger zone. That is, it is entering into the ultimate strain value. The ultimate strain value of concrete is 0.0035. Why you have so much of difference? When you testing your cube strength, you will get some idealized curve FCK. When you test your member in a structure, that is the concrete in a structure, you may get some diminished value. This is called as 0.67 FCK. This 0.67, it denotes size effect. When you check your concrete in laboratory, it is different because you will ensure some compaction, some good amount of vibration also. So you will get good strength what you are expecting. Whereas in your structure, you may have beams, columns and footing. You can't properly ensure vibration in some elements. That's why due to size effect, Some beam may be smaller in size, some will be larger in size. You can't ensure the real FCK value. So due to size effect, your curve may get 0.6 FCK value. This is your maximum value in your structure. When you going for design, we are giving the partial safety factor for your concrete. So this 0.67 FCK divided by your 1.5 is nothing but partial safety factor for concrete. Now for the design curve, you will get 0.446 FCK. Your FCK value will be around 0.45 FCK. This is the stress strain curve for the concrete. You need to have the stress block with 0.45 FCK with a strain block of ultimate strain 0.0035 and the proof strain, this is nothing but proof strain of 0.002. Till the proof strain, it will show you a parabolic nature. After that, the strain will be increasing. You don't have any increase in your stress levels. Okay. Now, we'll see the stress strain curve. Stress strain curve for steel. The same curve, x-axis strain will be there and y-axis stress will be there. You can see the difference. For the steel member, it will be linear till the yield point is reaching, it will be the linear. So after yield point, it will be subjected to drastically yielding. It will show you some parabolic curve. After getting your ultimate level, it will be drastically changing down. You can see here, this is the linear variation. After that, after the yield point, you may have some characteristic curve. This curve is characteristic curve, that is Fy, the real strength. For the design curve, we are dividing your characteristic curve divided by partial safety factor of your steel. You will get 0.87 Fy. It may be around here. 0.87 Fy. It may be around here. When you take a value, you will take epsilon y as strain 0.87 Fy divided by your Young's modulus of your steel value. You can calculate the strain at a point here and you can get a stress of 0.87 Fy for a mild steel bar. Okay. These are some of the terminologies, mainly the characteristic strength, characteristic load, partial safety factor for a material for concrete and steel, and the partial safety factor for the loads. That is, when you have the combination of load occurring in your structure, the dead load, live load and wind load, we can have a partial safety factor for that also. Okay. Now we are going to see about analysis of limit state method. We are going to see about the stress block parameters today. Stress block parameters, it is under limit state method, LSM. We can shortly calling it as LSM. This is your beam of breadth B and your depth D. The total depth may be capital D and your effective depth may be small d. You can rightly calculate your effective depth from the top fiber till the centroidal line of your steel. Here I am showing you the steel in only one part, that is, you can call it as singly reinforced section. Now here, as in same way as working stress method, the depth of the neutral axis may be XU. There we can denote it as X, here XU. Now below that neutral axis to the centroidal line of steel, it is D minus XU. When you draw a strain profile, the strain profile, the ultimate strain where we have seen 0.0035, it is your ultimate strain. Then somewhere here you will get some proof strain 0.002. Then it will be drastically changing, drop down to 0. Then again it will be changing here. Here for the steel, it is being governed. Here the tension part is not taken care by the concrete. The tension part is taken care by the steel. This concrete will be transformed to your equivalent area of your steel here. That's why your proof strain 0.002 plus 0.87 times Fy divided by Es. This is your strain at your proof strain level. So 0.87 0.002 till this EY plus 0.002. This is your strain profile for your singly reinforced section. Now you can draw your stress block. This is the ultimate value where you will get 0.45 FCK. From here you will have some drastic changes in linear form. You have a curve in linear form. After the proof strain, where you have seen in the graph, you will have some parabolic fashion of variation of your stresses. So 0.45, it is your ultimate strength of the material, then it will be drastically changing in parabolic form. Here in the steel, the stress will be around 0.87 Fy, that is your design stress. This is your C1, this is your C2, your ultimate is CS, it is acting at the distance of x bar. This x bar at the center, it will be acting at 3/7 of XU from the top and at the bottom 4/7 of XU from the neutral axis region. So this C will be acting at the distance of 3/7 of XU and at the bottom it is 4/7 of XU. Okay, when you take the compression, Cu, the ultimate, is equal to C1 plus C2. This is the stress block values for limit state method of singly reinforced section and the strain block for the limit state method of singly reinforced section. Okay. In limit state method, we also see some types of sections involved in it. It may be balanced section, under reinforced section and over reinforced section. For the balanced section, the neutral axis will be XU max, that is your critical neutral axis value. You can take it as balanced neutral axis. For the strain, this is epsilon Cu, this is your ultimate strain 0.0035. At the level of steel, you will get epsilon S, that is epsilon Sy at the yield point 0.002 plus epsilon Y divided by Es. Okay. When it is under reinforced section, when your AST is less than AST limit, what is your AST limit? When it is less than your AST limit, you can call it as under reinforced section. The strain block will be epsilon Cu, this is your ultimate strain. Your neutral axis value will be your actual neutral axis value pertaining to your under reinforced section is Xu, whereas this is your balanced section value Xu max. You will get strain around epsilon Sy. This epsilon Sy, this is for your under reinforced section, which will be lesser than your ultimate strain. Okay, then you can check that for under reinforced section, your neutral axis is moving forward, moving towards the top. Then when the section is over reinforced is nothing but AST provided is greater than the AST limit. For that, your strain will be greater than your epsilon S, will be less than your epsilon Sy, or epsilon Sy is more, so that we can check whether the section is balanced, under reinforced or over reinforced section. Okay. Today, so far we have seen about what are the methods involved in limit state method, what are the types of limit state, then what are the terminologies involved for the analysis of limit state method, then how to draw a stress block and strain block for limit state method, then what are the types of sections involved in limit state method. Next lecture we will see about how far we are doing analysis for singly reinforced and doubly reinforced beam and for one-way and two-way slabs. Thank you.